expressing solution concentrations. We're mostly going to talk about quantitative measures, but in addition to the ideas of saturated and unsaturated, we can also talk about dilute and concentrated solutions. And these mean the same things as they do in everyday life. A dilute solution is going to have a little bit of solute dissolved in it, and a concentrated solution is going to have a lot. So if you think about buying frozen orange juice concentrate, right, the little can, that's a concentrated solution. And when you add more water to it, you make a dilute solution, and then you have drinkable orange juice. So this is a table kind of summarizing a bunch of different solution concentrations. And we'll talk about each of these separately. So molarity, we've already learned about this. Molarity is the amount of solute in moles divided by the volume of solution in liters. If we change the temperature, the moles of solute do not change, but the volume of the solution does, because the density of a liquid changes a little bit with temperature. So the volume's going to change. The volume's going to increase a little bit, which means that as you increase the temperature, the molarity will decrease. Most of the time, that's not really much of a problem, but there are situations where that does cause a problem. And that, as far as I can tell, is the only reason that molality exists. Molality is not a typo. Molality, yes, they're very, very similar. This is the amount of solute in moles, but instead of dividing by the volume of the solution, we're dividing by the mass of the solvent. The mass of the solvent in kilograms. Well, if you have 1 kilogram of water, that has a volume of 1 liter. And so the molality is typically very close to the same number as the molarity, but the molality does not change with temperature. Molality is abbreviated with a lowercase italicized m, which you don't want to confuse that with the non-italicized lowercase m, which means meters. Parts by mass, there's a bunch of these. So parts by mass, we're talking about the mass of the solute divided by the mass of the solution. So if this is percent, it's the mass of solute divided by the mass of solution times 100. And percent is always the part that you're interested in divided by the whole thing, and times 100. Percent is per 100, right? Percent means per 100. So solute mass divided by solution mass times 100. If we have a mass percent here, 14% by mass, well, that means that there are 14 grams of solute per 100 grams of solution. So there are some related parts by mass units, parts per million and parts per billion. So instead of multiplying by 100 for percent, we're going to multiply by 1,000,000 or by 1,000,000,000. If we have a concentration of 15 parts per billion, that means there's 15 parts per billion parts. Well, you can use any mass unit that you want here. You can use grams or milligrams or kilograms. You can even use English units, ounces or pounds, because whatever unit is on the top just needs to be the same as on the bottom, and they're going to cancel out. You can also do parts by volume. Here we're looking, instead of the masses, we're looking at the volumes. The volume of the solute divided by the volume of the solution. So 22% ethanol would be 22 milliliters of ethanol per 100 milliliters of solution. And again, you could use a different volume unit if that was more convenient. You could use liters or microliters. It doesn't matter. So let's do this problem. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. A lot of these concentration problems really are just dimensional analysis. So we're given some numbers. The 12 ounces there is just to give you an idea of how much 355 milliliters is. 355 milliliters is like a can of soda. And what we're looking for is the mass of sucrose. So I'm going to take those numbers and I'm going to write them down. So I have 355 milliliters. But solutions have two parts, right? There's the solute and the solvent, and then we can also look at the whole thing together, the solution. And so this volume, is this the volume of the solute, the solvent, or the solution? It's 355 milliliters of a soft drink. It's the solution, right? So this is our solution. The solution is the water and the sugar, right? And then they're telling us 11.5% sucrose. What does 11.5% mean? Means 11.5 per 100. 11.5, this is mass, so 11.5 grams of the solute, sucrose, per 100 grams of the solution. This is a lot faster, and this is how it's usually written out, but it's going to be harder to do calculations with it like that, so I'd encourage you to write it down this way, because then you're really seeing what's going on here. And then we have a density, and the density is written with a horizontal fraction, but when we're writing it out here, we want to write it as a vertical fraction, grams over milliliters. Now, it doesn't specifically say what that is the density of, but what do you think it is? Soft drink, or the sucrose, or the water? The soft drink, right? Because pure water is most likely going to be 1 gram, and this is a little above because it's got sugar dissolved in it. So this is 1.04 grams of solution per milliliter of solution. Most of the time we don't need to be so careful to label all of these things, but when we're talking about concentrations, it can make things a lot easier. Okay, so that's everything I was given, and I'm trying to find the mass of sucrose. So gram is a convenient unit of mass. So I'm trying to find grams of sucrose. And then sometimes it can be tricky to figure out which of these numbers am I starting with and which one do I have to use as a conversion factor. So both of these are fractions. And when we say them, they both have the word per, right? 11.5%, right? 1.04 grams per milliliters. These are conversion factors. So this is the only one that's not a conversion factor. I'm going to start with that. So I'm starting with a volume of solution, and I'm trying to get to a mass of solute. So I have the conversion factors I need here, and I just need to figure out how to stick them together. Well, here's milliliters, and this one doesn't have milliliters in it. This one has milliliters of solution. This allows me to convert between milliliters of solution and grams of solution. So I can go from milliliters of solution to grams of solution using the density. And then I'm looking for something that's going to relate grams of solution to grams of sucrose. Well, this one has grams of solution and grams of sucrose. So I can do that. And there's my path. That's the hard part. $355 milliliters. I'm going to abbreviate solution. Milliliters of solution. And we're going to convert that to grams of solution. And then we're going to convert that to grams of sucrose. So that's my path. Milliliters of solution, grams of solution, grams of sucrose. Milliliters of solution, grams of solution, grams of sucrose. I need this unit to go away, so I'm going to divide by that. Milliliters of solution. So those units cancel out. And then I need grams of solution to go away. So I'm going to divide by that. And I get all my units to work out. Then my units are going to tell me where to put all these numbers. This one, grams and milliliters of solution, is the density. And it's 1.04 grams, so 1.04 grams per milliliter. And if it bothers you that there's not a number down there, that would be per 1 milliliter. This one then, I've got grams of sucrose and grams of solution. That's going to be my mass percent. And so it's 11.5 grams of sucrose, 11.5, and 100 grams of solution. And then I just do the math. So 355 times 1.04 times 11.5 divided by 100. Calculator says 42.458. And my smallest number of sig figs is 3, so this is going to be 42.5 grams of sucrose. Any questions? Do you remember when we made the salt solutions in the little volumetric flasks and then we weighed them and did the densities? The original solution, you weighed out 15 grams of sodium chloride, right? And you had to use a beaker to do it because it was too much really to fit on the weighing paper. It was quite a lot of sodium chloride, right? 42 grams of sugar is going to be roughly 3 times the size of that 15 grams of sodium chloride. That's quite a lot of sugar in 1 can of soda, huh? Any questions? One place that we often see parts per billion, parts per million is each household gets a water report from the city showing all the analysis of the water and the various things that are in the water and what their concentrations are. So here, the water sample is found to contain a pollutant, chlorobenzene, and it has a concentration of 15 parts per billion by mass. So this is asking what volume of this water would contain 5 times 10 to the 2 milligrams of chlorobenzene. Assume a density of 1 gram per milliliter. So again, let's highlight the numbers and highlight the question and the volume of water. So 15 parts per billion, and I'm just going to call chlorobenzene CB because we really don't care about its chemical formula here, and I don't want to write all of that out. What does parts per billion mean? Oops. 15 parts per billion means 15 parts per billion parts. So 15 per billion, billion is 10 to the 9. And it says it's by mass, so we need a mass unit here. I'm going to use grams, because that's just what we usually use. So that means we have 15 grams of chlorobenzene per 10 to the 9th grams of the water. And here by water, we're talking about the solution, not the that is pure water. Then we're also given 5.00 times 10 to the 2 milligrams of chlorobenzene, and we have a density of 1.00 grams per milliliter. Well, this is the density of the water. It has chlorobenzene in it, and when you add stuff to water, that increases the density, but this has a teeny, teeny, tiny, tiny amount, and so the density is still 1. So this is 1 gram of water per milliliter of water. And we're trying to find volume of water. Let's do liters. So what number am I starting with? 15? 5 times 10 to the 2, or 1? I'm going to start with that 5 times 10 to the 2 because there's nothing else I can do with it. I can't make that into, it's not a conversion factor. It just kind of is what it is. So I'm trying to get from milligrams of chlorobenzene to liters of water. I have to figure out how I can get there. Well, we're starting out with a mass of chlorobenzene. This has mass of chlorobenzene in it, but it's grams, not milligrams. So I could convert my milligrams to grams of chlorobenzene, and then I could use this concentration to convert to grams of water. My density relates grams of water to milliliters of water, so that would allow me to convert to milliliters of water. And then I can use my knowledge of metric units to convert that to liters. It can be tempting to just skip this part and just dig in and start calculating. And once you get good at it, you can do that. But if you're not good at it yet, you're just going to struggle and muddle around. So really, you need to lay out a plan, a path for your calculation, and then all you have to do is follow it. So we're going to start over here. 5.00 times 10 to the 2 milligrams of chlorobenzene. And then I'm converting that to grams of chlorobenzene. And then I'm converting that to grams of water. And then I'm converting that to milliliters of water. And finally to liters of water. Milligrams to grams to grams to milliliters to liters. Milligrams, grams, grams, milliliters, liters. And this is the same thing we've been doing with stoichiometry. We just use this all over the place. Dimensional analysis. So I want those units to cancel out. I'm going to divide by that. I need grams of chlorobenzene to cancel out. I need grams of water to cancel out. I need milliliters of water to cancel out. So I get all the units in there, and then I'm going to stick the numbers in. So converting between grams and milligrams, I need to know, what does milli stand for? 10 to the negative 3, right? So if I have one, yeah, too much water is bad for you. Everything's toxic if you get too much. Too much oxygen will kill you too. So, right, we're all just doomed. Or you could say, well, you know,
Right amount.
it's all about the right amount. Moderation, right? So a little bit of this thing in our drinking water, they've done studies, and this is probably not going to hurt us at all. But it gets too high, and now we need to be concerned about it.
Well,
Right.
Too much sunlight will, like,
Too much sunlight will,
bad
you
for
know.
you, and too little is not also
Yep.
for you.
And so one of my pet peeves as a chemistry instructor is that people freak out when they hear that there are chemicals in something.
Isn't that everything?
Okay, can you have chemical-free sunscreen? I've seen that, bottles. Chemical-free sunscreen. I'm like, what's in there? A vacuum? Right? Because if there was air in there, there's chemicals, right? Oxygen and nitrogen are chemicals, right? So chemical-free is just ridiculous, right? But the public eats it up because they're afraid of chemicals. Yeah, I'll get off my soapbox now.